Hello, so this series of videos is really going to deal with a more general approach to organic chemistry. So before we start in looking at organic compounds, we need to sort of know what that is, because you've probably heard the term organic most of your life referred to the way that food is grown. But in chemistry, organic compounds are simply the ones that are mainly comprised of carbon. There's other things that are in these compounds as well. Hydrogen's the other major component of them most times. But they can also contain oxygen, nitrogen, halogens, phosphorus, sulfur, and some other miscellaneous things. We can represent those types of compounds in various forms. Something you'll see quite often in a textbook is that of the space-filling model. So this can look a little bit like a bulb or something to that degree, because this is what's closer to reality. But we can't really see it very well because it's kind of blobby. The ball and stick model is what you more typically see, and it's more reminiscent of what we have like as an actual model that you have in model kits that we're going to talk about in a little bit. But these can be represented in drawings as well. Obviously, not my drawings very well, but in other people's drawings they can be represented pretty well. Usually you'll find that different colors here for the different balls mean different types of atoms. Next comes the dash and wedge form. What this is attempting to do is show you how things are represented in 3 dimensions on a sheet of paper. So how we read this is that the things that are straight lines are meant to be in line with the paper itself. So, for example, this right here looks like this. Okay, this and this are showing you that they are in line with the plane of the paper. So see how there's a plane that these 3 atoms can be on. You then have something behind that plane, and you have something in front of that plane. The atom that's behind that plane is represented by a dash. I always say, because once you're done with chemistry, you dash back home. So the dash goes back, which I don't, but if you do, dash back home, that is. This comes forward. That's represented as a wedge, and that's what those drawings mean. We can then talk about different ways of drawing things on paper as well. This is known as the expanded structural formula. That shows you that all carbons are present and where all the hydrogens are present also. Even though this is how we show them to just be able to see all of the atoms, it's important to note this is not how things are actually represented. Life doesn't live in 2 dimensions. We live in 3 dimensions, and we're going to talk about that in just a second as well. But that's not a 3D model. These are much closer to reality as far as where things are spatially, but this allows you to see things while you're working on paper. This actually could be the condensed structural formula. So this is a way of sort of naming something by reading it out. Okay, so this would be CH3CH3 because there's 1 carbon here with 3 hydrogens, 1 carbon here with 3 hydrogens, and so we would write it just like that. Now this is not the name, and we'll talk about the name in the next video, but this is a way to sort of write things out longhand. The easiest one for me to see, at least, is known as the Kukuli structure or line angle structural formula, and that is simply written like this. What does that represent? Well, every single time you have an end of the line right here, or a vertice here, 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 as well as this end of the line here, each of those points represents a carbon. We do not represent the hydrogen in these drawings simply because it's easier to see without all of that. That doesn't mean they're not there. Carbon bonds 4 times. So if something is not written there, then that means there's a hydrogen that's understood to be there. So for example, this carbon is bound once to this carbon. That means that there's 3 other bonds to hydrogen. This carbon has a bond to both that carbon and this carbon. So since it already has 2 bonds, there are 2 more to hydrogen that are not written in. Same with this carbon and this carbon. This has 2 hydrogens, this has 2 hydrogens, and here on the end, since there's only 1 bond to a carbon, 3 more are to hydrogen. So as we've seen, we can represent these simple alkanes multiple different ways. We need to learn how to name these, and this is absolutely something you need to know. This chain of just 1 carbon can be represented either way. This is called methane. Next we go to 2 carbons. That is called ethane. And we can actually write this as a line as well. Next we have 3 carbons, which is known as propane. 3 carbons can be represented this way or like that. Next we have 4 carbons, 1, 2, 3, 4. This is known as butane, 1, 2, 3, 4. Next we have pentane. This is 5 carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pentane. With 6 carbons, hexane. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All of those are the same exact molecule. Next we have heptane. 7 carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All the same. Next comes octane. 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Nonane is what we call a chain with 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know this gets tedious. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And finally, decane has 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so those are names that you definitely need to know moving forward. So why are we doing all these zigzag lines? Let me show you a model kit and maybe we can see that a little bit. If I try to take this 5 carbon line structure, so I've got 1, 2, 3, 4, 5 carbons. Well, remember that bonds and atoms are really made of electrons. And electrons don't like to be very close to each other because they repel one another, because each of them have negative charges on the outside, right? So really, all of these bonds, they're single bonds. See how they can rotate? Well, that's what's probably really happening if you have any energy around, and everything's constantly rotating, and that's very, very normal. But there's a more stable way that this molecule can arrange. It's what it wants to arrange as. And it wants to arrange in a way where atoms are far apart from each other so that they're not bumping into each other. Like if we start doing this, look at this. Even in a model kit, that ends up bumping into each other. The problem with that is that these are actually much smaller right now than they are in reality. So things tend to just not want to be like that. So if we keep playing around with how it is that things can be the furthest apart possible, what we find is that this sort of lets things spread out more. I'm going to rotate that some for you. So all the carbons are there in a row, and what we see is a zigzag pattern with those carbons, and that's kind of how we represent it, and that's kind of why we represent it that way. Okay, but it is important to also know if you move things and change that, that's still the same molecule. You still have the same number of carbons, it's just in a different arrangement, it's just rotated slightly. So something to keep in mind. Okay. Carbons can also cyclize. What that means is that they can make a circle. So I first have to remove 2 hydrogens because carbons can only bond 4 times. And then we can make a circle like this. Okay. Each of these has their own terminology and name as well. So if you have 3 carbons in a ring, that's known as cyclopropane. It could also be represented as 1, 2, 3 carbons like that in a circle or a ring. Next we would have cyclobutane. Next, and as this model kit is representing, that is cyclopentane. There and there. With 6 members in the ring, that's cyclohexane. And with 7, that's cyclooctane. So how many carbons do you think might be in cycloheptane? Let's go back to our previous chart. See how heptane is 7 carbons? Cycloheptane is simply 7 carbons in a ring.